Hello, this is Professor Kuehn. We've been talking about Pascal's physical treatises, and we've been looking at his introduction, and then we looked at the chapter in A Student's Guide, chapter 14, where he begins by talking about what's called the hydrostatic paradox. If we come over here, you'll see this is discussed on page 178 of A Student's Guide to the Great Physics Texts. And to remind you what the hydrostatic paradox is, if we have a column of water that has a depth h, let's say, and another column of water that has the same depth h, and they have openings on the bottom, each of which have the exact same cross-sectional area, then it takes the exact same force. F1 and F2 is the same. That is, it takes the same force to plug both of those water columns, even though the water column on the left might have, let's say, 10 pounds of water in it, and the water column on the right only has 1 ounce of water in it. So the question is, why is this the case? And I didn't say this last time, but let me add this. If we took another water column, let's say, that looked like this, and had a very wide base, but it had the exact same area opening on the bottom, and we filled it to the exact same height, perhaps this one might have 100 pounds of water in it. So if this one, let's say, had 10 pounds of water in it, this one only, let's say it has 1 pound of water in it, and this one, let's say, has 100 pounds of water in it. That if you took all 3 of these columns of water and you plugged them all, and you maybe glued these plugs in and you set them all on a scale, this one would weigh 10 pounds, this one would weigh 1 pound, and this one would weigh 100 pounds. Now if you take them off the scale and you suspend these and you allow these plugs to move, it would take a force F1 to hold this water in, F2 to hold this in, and F3 to hold this one in. And here's the neat thing, as long as the areas on the bottom are the same, then the force it takes to hold each of these in would be the same, and they would all be equal to the 10 pounds of water. So that is called the hydrostatic paradox. And what Pascal wants to do is explain why this is the case. And in order to explain this, he comes up with what we now know as Pascal's principle. But let me say one other thing before I go on to Pascal's principle. Let me draw another situation where, let's suppose we have a tub of water like this, full of water to some depth, and we have an opening here on the side, and this opening has some cross-sectional area A, and we try to plug it, and it takes some force to plug this. And if we took another column of water that was very narrow, let's suppose, and we had the exact same area hole on the side at the same depth, so we have the exact same depth from here to the location of the plug, it would take the exact same force to hold that plug in, like that. So in other words, it doesn't matter whether this plug is on the bottom of the column of water or if the plug is on the side of the column of water. In either case, it's going to take the exact same amount of force to hold it in. Or for that matter, you could take a column of water like this and put a hole on the top of it, like this. So we'll have, this is the plug right here, and it has some height of water from here, let's say, down to here. It's got some height. If that is the exact same height and this is the same area as that, it's going to take the exact same force. We'll call that F3, the force to hold that in. Provided the height is the same and the area is the same, then F1 is going to be equal to F2 is going to be equal to F3. That is the force it takes to plug this, no matter whether it's on the side or it's on the top, or for that matter, if it's on the bottom, it's going to take the exact same force to hold this in. So this, in sum, is the hydrostatic paradox. So the question is, why would this be the case? Now, if we look over to the next page, this is on page 142. These are the diagrams that Pascal is presenting us with. So you see up here, he's got this column of water. He imagines plugging it there. He's saying it doesn't matter if it's sloping, if it's a wide channel, if it's a sloping inward or very narrow channel, provided the heights are the same and the areas on the bottom are the same, then it's going to take the exact same force. That is Roman numerals 1, 2, 3, 4, and 5 will take the exact same amount of force to plug them. Now, how does Pascal approach this problem? Well, he considers cases like this, this, and this. So let's talk about these diagrams. So I'm going to clear this screen. Let me just open up a new one. Open up a new file. Save that one and open a new one. So let me do a couple more drawings that are related to these drawings he has here. So let's suppose that we have a box like this. And I think he mentions that in this box, we weld a tube and we weld another tube like this. Okay, I'm going to draw these boxes here. I'm still not very good at these kinds of drawings, as you can see. And we weld this tube right in there. This is a terrible drawing. And we put a piston in this one, and we put a piston in this one, plugging both of these holes. So this is water in here. Let's imagine this being water in this box. And we fill this one up to some height. And let's suppose you fill this to a certain height so that the weight of the water in this column is exactly 1 pound. So there's going to be 1 pound of force that is pushing down on this piston that's trying to make it go down. And the question is, how much weight do we need to put on over here in order to keep this plug right here from popping upward? Well, if that's 1 pound of force there, you can measure how much weight it takes. So let's imagine we put a little platform right here, and we set a copper block on top of this, and figure out how much weight it takes in order to plug it. Well, the interesting thing is because these two holes have different areas, it's going to not take 1 pound of force on this side, but instead it's going to take a larger weight on this side. So this might be a lead block, for example. If this is 1 pound, and let's suppose that this has a diameter so that the cross-sectional area on this side, area 1, is 1 square inch. And on this side, the diameter is such as, I know this isn't to scale, but let's say the diameter on this side, we'll call that area 2, has a cross-sectional area of 100 square inches. Well, you can measure how much weight you need to put on this in order to balance it, and it just so happens that it's going to take a 100 pound weight in order to balance that. If this is a 1 to 100 ratio of the areas, then it's going to take 100 pounds to balance 1 pound of water. Now, if we did the same kind of thing, we took a box, once again, the same box. Well, this is really difficult to draw with this tablet. Whoa. And we had this a certain height so that, again, I'll put a little piston in here. I'm not going to draw thickness of the box this time. We have the column high enough that you have 1 pound of water on this side. Well, we already said if this is an area 1 was 1 square inch, and area 2 was 100 square inches. I'm not going to write the square inches. We should just recognize that's 100 square inches and that's 1. We don't need a copper or a lead block. We could put water over here instead. So we'll put a piston in here and we pile water on it. Well, it happens that over here, it's balanced once again by 100 pounds of water. It doesn't matter. In other words, it doesn't matter if we use a lead block or a copper block or water. Whatever's over there needs to be 100 pounds. And notice there's a coincidence here that if there is 1 square inch of area over here and 100 square inches of area over here, and the height is such that there's 1 pound of water here, then the height is going to be such that there's 100 pounds of water over here. Now, as I mentioned before, if you have 1 pound of water, that is going to be about 28 cubic inches of water. So on the left-hand side, over here, the depth is going to be 28 inches. 28 inches deep. And over here, to have 100 pounds of water, well, once again, we need to have 2,800 cubic inches. And since the area is 100, that also is going to have the exact same depth of 28 inches. So there's this nice coincidence. This is all strictly empirical. That is, this is what you can find in the laboratory if you do this. If you have a box that's full of water, and you put 2 openings in the top, and one has an area of 1 square inch and one has an area of 100 square inches, then 1 pound of water on this side, that is 28 inches deep, will be balanced by happens, but we don't quite know why this happens, okay? Why is it that 100 pounds can balance 1 pound? And this is what Pascal is going to try to explain in the next couple of pages. And what he does is he tries to explain this in 3 ways. So let me give you a summary of what the 3 ways. The first way, he's going to think of this box of water as acting like a machine. The box of water acts as a machine for multiplying forces. This is going to explain why the heights are the same and why a 100-pound force can be balanced by a 100-pound force. So I'm going to explain why this would be the case. How does Pascal use this concept that this box of water is a machine in order to understand this, in order to explain this phenomenon? The second method he's going to use is he's going to talk about this in terms of Newton's third law, which is interesting because Newton wasn't even alive yet. So he uses the idea that when you have two parcels of water interacting with each other, that one pushes on the other as hard as the other pushes on one. So we'll come back to that in a minute, but he kind of has a premonition of Newton's third law here. And the third way he's going to explain it in terms of the center of gravity. So I'm just sketching out the three ways that he's going to try to explain this. Any one of these is going to work pretty well, but it's nice that he gives three different explanations for people who think about things in different ways. So let's take a look at his explanation of this phenomenon by treating the box of water as a machine for multiplying forces.